everyone. My name is Oscar Rendon, and today I will present our work titled Titanium Dioxide and Bended Ketosand PBA Nanofibrous Membranes, a Novel Approach for Efficient Methyl Orange Removal. A study focused on developing advanced composite nanomaterials for wastewater treatment application. About the background, industrial effluents, particularly from textile and food industries, often contain acidies, a class of pollens known for their toxicity, chemical stability, and resistance to biodegradation. Methyl orange, one of the most commonly used acidies, is highly recalcitrant to conventional treatment methods, making its removal a significant environmental challenge. Nanomaterials have emerged as promising tools due to their large specific surface area and to enable surface chemistry. Among them, ketosand, a biopolymer derived from ketene, is valued for its biocompatibility, biodegradability, and functional amino and hydroxyl groups that facilitate pollen absorption. However, pure ketosand suffers from low chemical and mechanical stability, which limit its use in industrial settings. Blending ketosand with polyvinyl alcohol (PVA) can overcome these limitations by improving flexibility, thermal stability, and mechanical strength. Moreover, incorporating titanium dioxide nanoparticles provide the material with photocatalytic properties. Under UV irradiation, titanium dioxide generates electron-hole pairs capable of producing reactive oxygen species (ROS), such as hydroxyl radicals, which effectively degrade organic contaminants. Our goal was to develop ketosand PVA nanofibrous membrane embedded with titanium dioxide nanoparticles using electrospinning and to evaluate their photocatalytic performance in degrading methyl orange from aqueous solution under UV irradiation. Ketosand was hydrolyzed in a 50% volume by volume acetic acid solution and blended with PVA in control ratios. Titanium dioxide nanoparticles were then incorporated at concentration of 1, 3, and 5% weight. The resulting solutions were electrospun by applying a high voltage to generate nanofibers deposited on a collector yielding porous membranes with a large surface area. Membranes were dried at 60 grades for 24 hours to remove solvent and stabilize at 25 degrees for another 24 hours to ensure structural integrity. About the characterizations, the FTIR spectra reveal the characteristic absorption bands of ketosand PVA and titanium dioxide, confirming the presence of all components in the membranes. The broad band at approximately 3,300 per centimeter correspond to OH and NH stretching vibration, indicative of strong hydrogen bonding within the ketosand PVA matrix. The band near 1,635 per centimeter was associated with amine first and carbon-oxygen stretching vibration, while peaks at 1,364 to 1,248 per centimeters correspond to carbon-nitrogen stretching and carbon-hydrogen bending vibration. Importantly, the band around 900 to 1,100 per centimeter assigned to titanium oxygen, titanium, and titanium oxygen carbon vibrations was more intense in samples with higher titanium dioxide loading, confirming the incorporation of titanium dioxide and its interaction with the polymeric network. This chemical bonding is significant because it prevents nanoparticle leachings during photocatalytic operation, increasing the stability and reusability of the membranes. about the photocatalytic degradation of methyl orange showed a direct relationship between titanium dioxide content and degradation efficiency. Pure Kidosan PBA membranes display only minor absorption of the dye, whereas the 1% titanium dioxide membrane reached approximately 17.5% degradation in 240 minutes, increasing to the titanium dioxide content to 3%, improved to removal efficiency to 91%, while the 50% titanium dioxide membrane achieved 96.6% degradation under the same conditions. These results highlight the synergistic effect of absorption by Kidosan and PBA and the strong oxidative capacity of titanium dioxide under UV. The degradation data fitted well to a cell first-order kinetic model as described by the Langmuir-Hischenwald equation. The rate constants key increased significantly with titanium dioxide content. The 5% titanium dioxide membrane exhibited a key value approximately 2.5 times higher than the 1% membrane, evidencing the critical role of titanium dioxide loading in accelerating the degeneration of reactive oxygen species, ROS. About the scanning electron microscopy revealed a uniform distribution of nanofibrous with interconnected pores, which is critical for maximizing pollen absorption and contact with active photocatalytic sites. Fiber diameters range from 120 to 180 nanometers for the pure Kidosan PBA membranes and increase slightly with titanium dioxide loading, reaching approximately 200 to 250 nanometers at 5% titanium dioxide. This increase in diameter is attributed to the higher viscosity and conductivity of the spinning solution when titanium dioxide nanoparticles are added. Furthermore, no significant agglomeration of titanium dioxide was observed at lower loadings, while a few localized clusters appear at 5%, although they did not compromise the membrane's porosity or surface area. About the energy dispersive X-ray spectroscopy confirmed the homogeneous distribution of titanium throughout the membranes as evidenced by strong titanium signals overlapping with the polymeric matrix. This uniform dispersion is crucial for exerting consistent photocatalytic activity across the entire surface of the membrane. Compared with pure Kidosan or other conventional membranes reported in the literature, the Kidosan PBI titanium dioxide nanofibrous membranes exhibit superior removal efficiency, faster kinetics, and improved mechanical stability. These findings underscore the potential of electrospun polymeric composites as multifunctional materials for advanced water treatment. Kidosan PBA nanofibrous membranes with embedded titanium dioxide nanoparticles were successfully produced via electrospinning, showing uniform fiber morphology and well-dispersed nanoparticles. Titanium dioxide significantly improved photocatalytic efficiency, achieving over 91% methyl orange degradation within 240 minutes, far surpassing pure Kidosan PBA membranes. FTIR, SEM, and EDS confirm the structural integrity and strong nanoparticle ensuring reusability and long-term stability. These membranes show great promise as sustainable for multifunctional nanocomposites for the treatment of industrial wastewater contaminated with persistent organic pollutions. Thank you so much for your attention.